Hello and welcome to the AIOH chapter meeting. Today we have Nathan Ost, who will be discussing reviewing the Australian workplace exposure standards. Over to you, Nathan.
Hi everyone, Nathan here. Just a brief introduction on video, then I'll jump to the slides. I've been an occupational hygiene, environmental health professional for over 20 years now. I have a couple of science degrees and I'm a full member of AIOH and a couple of other organisations. I coach my kids' soccer team and I'm a hobby musician with some music up on Netflix and a few other big commercials. So that's a little bit about me. I'm going to jump straight into the presentation. I will be stopping my video and you should see the presentation come up on your screens any second now. Obviously, you know, we're talking about the review of the Australian Workplace Exposure Standards. Lots to go through, so I'm going to jump straight in. Okay, some clarification firstly on this presentation. I'm talking about a condensed version of a set of complex concepts, processes, interactions, and I can't possibly cover everything with detail, and I may miss or skim over some of the topics or factors. The in-depth specifics and concepts can be discussed in another forum or offline with me. I hope you can appreciate that. I am only discussing the scientific aspects of the derivation of the derivation and recommendation of the workplace exposure standards, which I will refer to as WES, not policy or industry specifics. And I won't be discussing in depth or pretty much at all any of the methodology of measurements of the airborne contaminants. That's a topic for another presentation. So the objectives of this presentation is I hope everyone gets a better understanding of the overarching WES review methodology and some insight into the derivation of a WES. So the derivation is part of the methodology. And I just wanted to admit that it was a really daunting and difficult yet fun and fulfilling project that through some great WSP teamwork and excellent preparation and support from Safe Workers Australia, we managed it. We managed to get through 726 chemicals in just over a year with COVID thrown in to boot. I didn't want to mention that word. Okay, Bo, you just let me know if there's any issues with anything, and but I'll just keep going until then. So this is the flow of the presentation. I'm going to just do a quick look at history and background. So to place this in perspective, I'm going to talk a little bit about big history, but bear with me. There's a theme and a narrative that follows through, and where the workplace chemical hazards and exposure standards comes into play here. So big history, this is the big history timeline. Big history examines history from the Big Bang to present. Bear with me, guys. The key of big history that it searches for the universal patterns and trends or themes. So if we look right back here, Big Bang, after the first few moments, space, time, energy, hydrogen, helium, the four fundamental forces all exploded out. A few million years later, there were some heavier elements. We had some basic elements, so I'm leading into the chemical aspect here. Some heavier elements that formed in the furnace of second generation stars and novas. The theme is there's increasing complex as we go from right back there forward, so that increasing complexity. So this is kind of interesting. I found the formation of the large structures such as galaxies, stars and planets are dominated by gravity, one of the fundamental forces, which works on large scales. Think of the sun, the earth, that's some big kilometers there. Whereas we humans, life here, we're sort of more delicate, yet very complex packets of chemicals in one perspective. And the interactions of chemicals are dominated by the electromagnetic force, which operates in much smaller spaces. And that's why we're so much smaller than stars and planets. But that's a little bit off point. I'll keep going along. So the main point is that there's increasing complexity along the way. And just as gravity concentrated clouds of matter in the early universe, collective learning, this is an important part of where we're getting to, generated denser and more complex human societies and accelerated change, giving humans more control over our environments, including the workplaces. So, and right over here is the great safe workwears review, which I think will stay in the timelines and be discussed for eons into the future. We're all pretty aware of images like this from way back in the day. Industrial progress due to more complex societies, generated pollution and byproducts. Workers are exposed to hazards, and we being humans became aware of these hazards, and they were causing ill health, and that something needed to be done about it. So along my presentation, there's these light blue screens with important terms with a little download from the cloud item. These are the sort of terms that are, well, important, I guess. We're starting to look at toxicology 101 here. So remember, this is just the history, putting it all in perspective. So humans, we became aware of airborne chemical hazards thanks to collective learning. Things got more complex. These chemical hazards could enter the body through 3 main routes of exposure. That's how they're absorbed into the body. Through the respiratory tract, by breathing, uptake via the skin, and via the gastrointestinal tract once we ingest something. Some other important terms to clarify are exposure concentration and dose, and internal dose. So your exposure concentration is the amount in the media encountered in the environment, and what we're really dealing with here is the media is air in most cases. Now, internal dose is the amount of the substance taken up or absorbed by the body after exposure to those airborne concentrations, or the dose could be administered in a toxicological study in animals. Okay, so busy slide just gives a schematic, a pathway from exposure over here. Here's our 3 routes of exposure, showing modifying factors within populations and individuals, and the opportunities for interventions and or controls. And over here, before it becomes a dose, we have occupational health standards or exposure standards, and some of the controls that I know that you are all pretty aware of. But yeah, this is just to give a visual representation of this process. So I've touched on this. Historically, we recognize that airborne chemical hazards can result in ill health, and this drove the development of the exposure standards. What are exposure standards? I'm pretty sure most of you know, but the term exposure standard means an airborne concentration of an individual chemical substance within a worker's breather zone, which, according to current knowledge, and that's an important factor here, and current knowledge, it should not cause adverse health effects or undue discomfort. As we know, the workplace exposure standards play a key role in minimizing the risk of workplace illness. And I'm pretty sure most of you are aware that the standards come in 3 forms: your time-weighted average over 8 hours, 5 days a week for a working life of 40 years, and your acute or short-term values, your STEL, and your peak limitation. Still looking at a bit of background, bit of history, and we're not into the guts of it yet. Here's a timeline of exposure limits. They have different names and different meanings, but we're going to stick to WES in this presentation. So right back 140 years ago, there was a simple exposure standard for carbon monoxide about 140 years ago. But with that theme, with collective learning, and we moved forward and we produced more complex lists as we moved along, and sophisticated processes, which feeds into that first theme slide. We came to here, and this is what we're obviously concerned about today. So where are we at in this presentation? That was a quick run through the history and background. Let's have a look at some of this summary of the scientific aspects. Now, remember, some of this is can go pretty deep, but it's a summary that I'm presenting here. Blue screen, important terms to consider again. When deriving or establishing a standard, a key element is the critical effect. So the critical effect is the most sensitive adverse effect that occurs at the lowest airborne concentration and or dose. So an adverse effect generally means it causes harm. This can be to growth or development, to the lifespan or physiology or tissues. Adverse effects can or cannot be, or may or not be reversible. That means the effect goes away after exposure, irritation in some cases, but that still can be a critical effect. There are some non-adverse effects, which are sometimes termed adaptive effects, which are the body's response to maintaining homeostasis or maintaining the status quo, making sure you stay healthy. And some adaptive effects are liver weight changes, for example, as the liver metabolizes a toxicant. An important term is understanding what a local or systemic effect is. So that's based on the proximity of the site of exposure and the site of effect. So a local, which pretty self-explanatory, means if you're exposed via inhalation and you get irritation in the nose or at that point of contact, the effect is there. It's at that point of contact. A systemic effect means the effect is at an organ or tissue away from the point of contact. Oops. And there's some examples of some local and systemic effects. So what we have here on this left, this is a little bit busy, but is the cover page of one of the evaluation reports. Reports for vinyl chloride. So we established in regards to vinyl chloride that the critical effect of exposure is liver cancer. Now that's a non-reversible. Once you take the exposure away, the cancer doesn't go away unless via medical intervention, but that we're not concerned with that in this presentation. And it's a systemic effect by way of example because you breathe it in and the effect is in the liver, which is away from the lungs and or skin, if it's uptake by the skin. So that probably shouldn't say recap there, but the aim for the review of the WES is to develop health and risk-based WES. I'll expand on the difference between health and risk-based later. WES, health and risk-based WES and notations based on evaluation of the best available data for individual chemicals. So where does this data come from? Human data, that's, human data comes from studies in volunteers or clinical exposure studies. We get a bunch of healthy individuals, adults, and expose them to a chemical within specific policies and means that we're not killing them or doing permanent damage. We also get human data from case reports of accidents in industry or some non-accident poisoning situations. We also can source data from epidemiological studies. I won't delve into these now. That's another pretty deep, complex study that we can discuss at another point. But some of those you might be aware of: cross-sectional, cohort, perspective, looking forward, historical, and case control. So they're the main sources of human data. We also have animal data. This data usually comes from animal exposure studies, toxicological studies. You can break them down into pretty much two types. Single exposure studies where you're looking at acute effects. Some of the outcomes of that are your LD50s, your LC50s, which is a lethal dose to 50% of the group that have been exposed. Then there's also repeated exposure studies, and they're usually, that speaks for itself. The animals and groups of animals are repeatedly exposed over a certain amount of times, usually subchronic or chronic. Subchronic usually means around 90 days or 13 weeks. That's a subchronic study. And chronic, which is usually longer than 3 months, but that can depend on the species. And these are some of the sort of toxicity outcomes that will be measured or looked at. And we'll delve into these a bit further on. So we have this data, but there are some inter and intraspecies considerations when interpreting this data. There are species differences. So models are good predictors of toxic outcomes in humans, but species differences obviously are there. This is due to a lot of factors which may vary with the species in question. Say a rat, they're smaller in size, they have a shorter lifespan, they're prolific breeders than most humans, and they have different dietary requirements. That means we need to extrapolate. Because animals are commonly exposed to extremely high concentrations of test chemicals, by different routes of administration. They could be injected, it could be dietary, and that's for their entire lifetime, which often can be shorter than that of a human. The challenge is to extrapolate from the animal results to predict the effects in the human populations that may have and probably have very different exposure patterns. So some of the extrapolations are from high dose to low dose, from the test species type to humans, from one route of administration to routes that are relevant to human exposure. Usually with the animal studies, they're receiving a constant concentration, daily dosing regimes in the animal tests, and we need to extrapolate that to the discontinuous type of exposures that are common in human populations. We're not getting specific doses at every point in a day, etc. There's also human variability. Toxicity is often for some compounds age dependent. The younger and more immature the person, the more different the response is that of an adult. So in regards to the workplace exposure standards, we're not dealing with children, because the group are working adults, but there are also sensitive subgroups in the workforce, such as pregnant women. So there's some considerations when looking at the data. Some more important terms: dose response and a dose response relationship. And I will discuss these terms and concepts in the following slide in a bit more detail. More Tox 101, a point of departure, your nulls, your lols, that's the no observable adverse effects levels. There's also benchmark dose, and also the concepts in and around a threshold and a non-threshold dose response, or a carcinogenic and non-carcinogenic, threshold non-carcinogenic and non-threshold is a carcinogenic, which can get a little bit confusing sometimes. Okay, so here we're looking at a dose response curve for a chemical with a toxicity threshold. The dose is down here on the bottom. This is just arbitrary sort of values here, and the response is here on the y-axis. So the region of the dose response curve that marks the transition from no toxicity, so there's no toxicity, these two here, the marks from no toxicity to toxicity is called the threshold, and that's the threshold there. So the points of departure, the POD that I've got here, are the points on this curve corresponding to the estimated low effect level here, or a no effect level. Now, a no observable adverse effect level is the highest concentration at which no toxic response, adverse response has been measured. The LOL, which is the lowest observable adverse effect level, is the smallest concentration at which an adverse effect is observed. So that was a threshold curve. Sorry, I'll bounce back to that. This is a stylized dose response curve for both non-threshold, that's the linear line there, and the threshold-based chemicals. So this is the no effect level for the threshold. The main point in this is that the line for the non-threshold or carcinogen, the line goes through zero, and any small increase in dose is associated with some increase of risk. I'll put cancer there, but increased risk of outcome. But in this case, we'll say cancer. So even right down here, there's a small increase in risk of cancer. And obviously, the higher the dose, there's a larger increase in cancer. And we often have to extrapolate into the low dose range from the actual experimental dose range. So we got, just say there's some dose points up here. We have to extrapolate down there, and I'll explain that a bit further in this slide here. So here's the observed three dose points. That's observed. This is the lowest dose that we witnessed that caused cancer. Extrapolation, this is the extrapolation point, the line going through zero there. So this linear extrapolation through zero dose from the upper confidence level of the lowest dose, that's the confidence levels of these lines over the dose points. I won't talk more about that. Gives you the slope. Now this is the slope factor. we use the slope factor when deriving numbers for carcinogens. That's TWA values for carcinogens, and I'll talk more about that later. So, having said all that, there are a bunch of factors that need to be considered and looked at when deriving a workplace exposure standard. And there we go. There, I think where we are just under 20 minutes in, and if you're there, Bo, probably got time for one, maybe two questions if there are any.
Yes, we have one question, but can people please put the questions in the Q&A chat rather than just the standard chat, just so that we can take the most popular question from that. We have a question from Jonathan Lee. Are these studies, laboratory studies, engaged directly by SWA or existing studies from external sources such as ECHA? I hope I got that right, or ECHA.
Yeah, that was Lee, was it? Lee,
Jonathan Lee. So
Jonathan Lee. Sorry, Jonathan. To answer your question, the studies are in the part of the scientific literature, and the studies have already been conducted that known by various organisations or universities, and the studies were then used by some of the primary sources and secondary sources that I will talk about a bit later. So, no, Safe Work Australia did not conduct or contribute to the conduct of those animal studies. Probably time for one more quick one, Bo, if there is another one.
Yeah, I've got a question here from Peter. Can you please clarify the benchmark dose departure?
I couldn't do it right now. I apologise. That's can we maybe discuss that at another point? I apologise. It's probably will take too long at this point, but it's a similar dose response. It's based on percentages of response and extrapolating from that, similar to the slope before. I can address that a bit later if we get time.
Great, that was all.
Okay, thanks. So I'll move on. So we've looked at the history background. We've had a quick look at the summary aspects. Now I want to talk about the overarching review methodology. And that's not just deriving the values. This is the review methodology that Safe Work developed. Okay, so this is the overarching review methodology, as it says there. It was developed by Safe Work Australia with Health Canada. It was driven by the need to update the WES in bulk. So we had to be efficient but yet still robust. And the methodology, it was peer reviewed by local experts and Health Canada, and it was agreed by Safe Work Australia members in early 2018. So the main part is the main take home from this here in the overarching review is there's three parts to the methodology. I think I'll discuss that a little bit more further on there. On the if you go to the Safe Work website, you can find the guidance documentation on all of these. I'm pretty sure some of you may have had a look, but it discusses those three parts with more explanations, more deeper, bigger explanations. Just also remember that you can provide feedback on the draft evaluations, but remember, Safe Work Australia are only seeking feedback on the science at this point, the scientific specifics as to the derivation. Okay, actually, I will go back. First part of the overarching review is identifying which data sources we were to use in the derivation and listing those sources as primary and secondary. The second part of the overall review methodology was to list which airborne contaminants needed to be reviewed. And the third part, which is the sort of nuts and bolts, is getting the numbers and the combinations, was to derive the WES from for the list of airborne contaminants, the identified contaminants, via the trusted sources. WSP were not involved in this part 1 and 2. Our main project was part 3. And that's what I'll actually expand a bit here. Part 1, here are the primary data sources. Now, these form the basis of the decision-making for recommending a WES. for the airborne contaminant. So this is where, Jonathan, you asked before about the studies. These sources would have did some reviews and literature reviews and had all that science within their review documents, and we use that as a primary source of data. There were certain criteria that had to be met for Safe Work to choose these primary sources. These are the secondary sources. These were used where there were significant, there were data gaps, or when we used a weight of evidence approach due to uncertainty in the primary sources. So we had these secondary sources. So remember, there's 3 parts to the overarching methodology. The second part was picking which chemicals need to be evaluated. Again, we, WSP, weren't involved in this selection process, and I'm not 100% sure about these numbers, but I'm pretty sure that there were 644 chemicals on the WES list in 2018. There ended up being 726 evaluations undertaken. So there were some added to that, obviously added to that 644. So part 3 of the overarching methodology is recommending WES. It's the nuts and bolts. It's us, how we come up with the numbers and why we did. And that's what I'm going to talk about next. So, Bo, you there? Probably some questions about that overarching methodology. I can't really speak too much to it, but I guess it's a point for questions either about some of the science prior as well. We've got a fair bit of time, 25 minutes in so far.
I've got a question from Will O'Callaghan. How will SWA communicate the WES updates once finalised, i.e. in one communication or WES or by WES? Any idea on when, e.g. before the end of the year?
G'day, Will. I'm not 100% sure on how Safe Work will communicate, if it's going to be in one batch. I can't take a guess, maybe in the different groups. Apologies there, I'm not privy to that information, but I do understand that we're hopefully looking at before the end of the year to have everything updated. Hope that helps. One more question, Bo, if you have one.
Yep, sorry.
You're right.
From Chris Sparks, as a hygienist in the US with responsibility in Australia, are the WES regulatory standards or industry guidelines?
The WES are a part of the model. Ooh, you got me here. Part of the model set by Safe Work Australia, which the states of Australia can and maybe should. Apologies, bit slack on this point. Should take up. So maybe someone else might be able to elaborate better on that than me. I'm a science boffin in the background here. Apologies for that, Will. We can look into that a bit further at another point. I'm going to have to move on now, Bo, so I'll push forward there. Sorry about that, Will. Where are we at? So we're going to look at the WES evaluation process. How did we come up with the numbers? So how are the WES values determined via the methodology, but via part 3 of the overarching methodology? Just reading from the slide, the WES value is determined by using information from those trusted sources that were picked, that were selected in part 1 of the overarching methodology. We had to consider the TWA's, stells and peak limitations from the primary sources, and also the toxicological and epi data that was used to establish those WES from the trusted sources. We had to determine the critical effect and any information on the dose response relationship, including the points of this departure. We were not undertaking extensive literature reviews. And I think this goes back to Jonathan's question. We were not examining the original reports used by the trusted sources, the primary and secondary sources. We were only using the information as presented by those sources. And any decision we made had to be clearly articulated and justified in the evaluation report, giving the constrictions of time and space. So now I'm going to go just a quick look at the evaluation report. This is a blank template. This is how we received it. The cover page. So this is the cover page. This is where the chemical specific information is recorded. I'm pretty sure some of you are reasonably familiar with some of these now, where the recommendations are made, where the summary of the information and data was presented. Then there was 3 appendices. So the appendix is where all the relevant data from the primary and secondary sources. As you see here, here's the primary sources. We'd fill that out, put in the their standard, and here was the secondary reports that were relied upon. And the other two pages, following pages, was information around carcinogenicity, the notation, the skin notations, and other information. Now, Safe Work Australia provided really great detailed flowcharts that really helped us with the evaluation. It's busy. I'm not going to go through this in any particular. You know, they were great for the evaluation, but not good for a presentation. So I've summarised this in the next slide. But just note there's 5 stages in part 3. 5 stages. Stage 1, 2, 3, 4, and 5, which I'll elaborate on a bit further. So, stage 1 over here. Stage 1 is the assessment of whether the chemical is a non-threshold based genotoxic carcinogen. If it is, we go on and we derive it, the TWA. If not, we move on to the stage 2. I just had a pop-up, sorry, I just moved that. So stage 2 was to evaluate or recommend a TWA for non-carcinogens. That's a stage 2 here. Stage 3, if there was stage 3, I'll just move over to the acute wares. Stage 3 was undertaken to evaluate a short-term or acute limit. If the primary sources didn't have a STEL or peak that's included in Safe Work Australia, we went straight to stage 5, but I'll discuss that a bit further later. So across here is stage 3, evaluating for acute or short-term, as mentioned. And then say we came up with a TWA and a peak. We had to decide on what combinations were best. So that was stage 4. Then after stage 4, back across to stage 5. Now you'll see that if there was no acute wares to be evaluated, straight to notations. And same with the carcinogens, the non-threshold based genotoxic carcinogens. That went straight to notations. I'm about to talk about this stage here, stage 1 and 1A and 1B. Okay, establishing if a chemical is a non-threshold based genotoxic carcinogen. So there were 3 criteria: mutagenicity, carcinogenicity, and genotoxic mechanisms of action. So criteria 1, there had to be clear and unambiguous positive results from adequately conducted mutagenicity tests, and I'll expand on these in a bit in a moment. There had to be positive results from adequately conducted carcinogenicity studies, and point 3 here, it had to be assumed or confirmed genotoxic mechanisms of action in the formation of tumours. Now, criteria 1 and 2 were a must, but for some chemicals there was insufficient data on the mechanism of action of tumour formation. The chemicals that ticked 1 and 2, and we didn't quite know about 3, they were assumed to be genotoxic carcinogens until proven elsewise. Erring on the side of safety there. So here's I guess a hierarchy or a flow chart of that process. We were primarily involved with these red thick arrows down to the non-threshold in understanding if the chemical is a non-threshold based genotoxic carcinogen. So tumours Tumours can arise due to a genotoxic or non-genotoxic mechanism of action. Genotoxic is a broad term applied to agents that or chemicals that damage the genetic information, that is your DNA or your chromosomes. There are some non-genotoxic mechanisms, not genotoxic, non-genotoxic mechanisms that can result in cancer or tumour formation. And some of these include hormonal changes, chronic irritation, chronic inflammation, immunosuppression, etc. So your genotoxic compounds can be further divided into mutagens, mutagenicity, and classigens or antigens. So mutagens are DNA part of the genetic material information. Mutagens are DNA reactive substances that have the potential to directly cause DNA damage. And they're generally detected in bacterial reverse mutation assays. So the other side are the classigens and antigens. They impact the chromosomes. Now, got a bit forward there. Just moving on there. In the case of these here, carcinogenicity by these mechanisms is generally considered to have a biologically plausible threshold. So we didn't pursue that avenue. Okay, so here's another one of Safe Work Australia's provided great detailed charts, as mentioned, great for our evaluation and helped us along the way. A lot of yes and no's and along here, but I'm not going to go into that to any detail for this presentation. What I will do is give you a little example. So this is vinyl chloride monomer. Here's the evaluation cover. On this left-hand side here is the cover page. The critical effect is liver cancer, as we mentioned before. Vinyl chloride is considered a human carcinogen based on unequivocal results in epidemiological studies. So those three criteria for determining a non-threshold based genotoxic carcinogen: mutagenicity, carcinogenicity, and a mechanism. So here's the appendix of vinyl chloride, and you see this is the information re-extracted from the ACGIH, and epidemiological studies comes under the human data subtitle here. So there was unequivocal results saying yes, it's carcinogenic. On the next page, I'll have some animal data, but here in the green is the mutagenicity. It was reported in both in vitro, which is cell lines, and in vivo, which is in live whole organisms. And there was a mechanism is likely to act by a mutagenetic mode of action, and that information came from these primary sources and secondary sources as well. We got ACGIH, DFG, which is the Germans. So for the purpose of this assessment, vinyl chloride is assumed to be a non-threshold based genotoxic carcinogen. This is the same cover page for vinyl chloride. This is the follow-on from the ACGIH appendix, and here's the animal data. There was even evidence within animals to say yes, it causes liver cancers, sarcomas. Here's the mutagenicity data here, evidence here. I won't go into them too much, but there was evidence that it was a mutagen, and there was no evidence to the contrary as to its genotoxic mechanism. Also of note, some of the primary sources wouldn't assign values if a chemical was genotoxic or exhibited carcinogenic properties. I hope that made a little bit of sense there, and I'll move on a bit. So we've established that vinyl chloride, where we're assuming that it is a non-threshold based genotoxic carcinogen. How do we get to this number? It's pretty low. I know lots of people shaking their heads about that probably out there. Talking about the sample analysis, there is uncertainty in quantifying that, but that was beyond any further beyond that was beyond our scope. So we can't discuss that at this point. Well, I won't be anyway. So how did we come to that number? So if it is a non-threshold chemical, we had to calculate the TWA value, the concentration, based on a minimal cancer risk, which is equivalent to 1 in 100,000 risk, which is deemed acceptable based on Australian policy decisions. And I won't go too deep into that. That's another topic that we can discuss for a long time. So I mentioned before there was health-based and risk-based TWAs or WES. This is a risk-based because we're basing it on a risk value, not a definite threshold health outcome. This is risk-based, even though there is a health adverse health outcome in cancer, but it is risk-based. So how did we do this? We were using either cancer slope factors or inhalation unit risk factors, which are similar, and we source them from the US EPA. But we had to adjust for workplace frequency, duration. So here's some important terms again. I just mentioned those then. Cancer slope factor. So the cancer slope factor, I will expand this and show you how that's derived in a moment. But that is the estimate of the increased risk of cancer from exposure to a dose. If you look here, milligrams per kilogram per day, it's risk per milligram per kilogram per day. So it's a dose, it's internal. Usually from oral studies. It's the excess risk if you're exposed to 1 milligram per kilogram per day for a lifetime. Now, the inhalation unit risk is a similar concept, but it's for a concentration. It's excess risk per microgram per meter cube per day, or it might be milligram, but we'll stick with microgram. So the cancer slope factor or the inhalation unit slope unit risk factor can be multiplied by an estimate of the lifetime exposure, which is in milligrams per kilogram per day, to estimate the lifetime cancer risk. So if we have milligrams per kilogram per day times a risk per milligram per kilogram per day, we end up with risk because these units cancel out. Same with inhalation unit risk. So these, when the US EPA derived these relate to lifetime continuous exposure. That's 70 years average lifetime. We need to adjust for a working lifetime, which is, I think it's 40 years, 8 hours a day, some other factors there, but we'll talk about that in a second. So this slide here shows you, the next one coming up discusses the slope factors and how they're derived. So there's the dose response curve. There's the actual test results. Well, that went too quick for me. I wasn't supposed to do it that quick. Anyway, so here's the observed test results. There's 3 doses there. This is the lowest dose that caused cancer. A line was drawn down through 0. This is done mathematically, but this is a visual representation through 0. So that's the linear extrapolation through the 0 threshold down here to the upper confidence level of the lowest dose that caused cancer over here, and we get a slope. And again, this is I think maybe we discussed it before, but anyway, that's the visual concept of the cancer slope and inhalation units risks. So this is stylized. Here's just a visual representation. Again, here's the slope, the extrapolated, say, cancer slope factor. On the y-axis, we have risk of cancer. Down here, we have concentration. If we get that acceptable risk on this y-axis at 1 in 100,000, we draw it across, we can come up with a concentration. This isn't how it's done. This is just to give you a visual cue for the concept. So say we had more of a risk, because this is increasing risk up, more of a risk, say 1 in 10,000 or 10 in 100,000, that's up this side. If you draw a line across, drop it down, it's at a higher concentration. The more you're exposed to, the more risk of cancer there is. Remember, this is a non-threshold based genotoxic carcinogen. We're not talking about the threshold. I'll talk about them in a second. And that's vice versa. If you exposed to a small, a less concentration than there, you've got less risk of cancer. It's pretty straightforward, pretty simple to digest. Now, these were the calculations. I'm not going to go through these in any detail right now. I'll point out this is the working lifetime adjustment here, 40 over 70 years, so here's the continuous, 70 years, 24 hours a day, 365, adjusted for 40 years, 8 hours a day, 240 days. If you go to the guidelines on the website, this is all explained a bit better, or we can discuss these offline for those who want to get deep into this part of it. If you have a bit of nous, you can build a simple Excel model using those equations, which I did do prior to taking on getting into the project, but Safe Work Australia provided one that they had prepared early, which made it much easier, as you can see there, and they were great help, and it was amazing. So we've had a look at stage one, the carcinogen and how to derive it. Sometimes there is no cancer slopes or inhalation unit risk, and to derive a TWA there is via a different method, and sometimes we couldn't. That's pretty complex, so I can't cover that today, but maybe at another point. So now we're going to move along. Say the chemical in question that we're evaluating is not a carcinogen or non-threshold based genotoxic carcinogen. We're going to look at stage 2 now, and we've gone backwards there. Flowcharts again, there were 3. This is just for the non-carcinogen TWAs. There are 3 of this caliber and more. I'm not going to go through these. Again, lots of great flowcharts that helped guide us in the process of deriving values. So, excuse my breath there. Here, what I'm about to present here is the summarized instructions from the guidance material and the flowcharts. So this is how we derive a TWA value for chemicals that are not non-threshold based genotoxic carcinogens. If all the primary agencies, the primary sources that we mentioned before, have the same TWA, now we're just dealing with TWA, we're not looking at the acute values yet, the stellar, the peak, that value will be recommended, and that would be put forward. And they all had the same for those that presented one. If the TWA values from the primary sources are not the same, a weight of evidence approach was taken to decide the WES parameter and the value that best reflects the data. So these non-carcinogens, this weight of approach, they were derived from the point of departure on the concentration response or dose response curve. I've been using dose response, but concentration response curve for the critical effect. Remember, we established that before, which is established from experimental observational data. So we used a point of departure, say the null or the lol, and derived a number based on that for the critical effect. We had to provide a justification as to why and how. I'll quickly give an example about this process in a second, but the other outcome is that neither Safe Work or any of the primary agencies have a TWA value. So that was we're talking about stage 2. So we'd skip and go on to stage 3. So none of the sources had a TWA. We just go straight to the acute values, the acute WES. Okay, so this is how we derived or recommended TWAs for threshold-based chemicals. Important term, again, uncertainty factors. So uncertainty factors are factors, 10 or more, that apply to the point of departure, the null, the no observed adverse effect level, or lol if there isn't a null, whatever point of departure for the critical effect, to provide a margin of safety to account for the uncertainties in the studies. Now, we sort of discussed the considerations and uncertainties between animal and human data a little bit before we touched on that. And here's a visual representation. I showed this threshold dose response curve before. Here's our point of departure here, say for X chemical. This is the no observable adverse effect concentration down here at 10. Uncertainty factor is a factor just simply applied to this value here to account for the uncertainties in the species or the duration, and we can come up with a TWA. Here is this table is some sort of general rule of thumb uncertainty adjustment factors. This is sort of in the toxicological, epidemiological world. This wasn't directly provided by SafeWork. I forgot to mention that in the process there was a third-party reviewer who we would do the draft reports and send them on, and the reviewer would provide comment. So here's some of the factors. Just think if you applied every one of them, you'd end up with a really large and unrealistic adjustment. So some judgment had to be applied in that. So, okay, this is another example report. Here's the front cover page on the left-hand side of your screens here with all the summary data, and here's the appendix with the primary source, the ACGIH. Note that the TWAs are different, 220, and here's 200 down here from the Netherlands, the Dutch. So therefore we had to apply weight of evidence approach. So the no observed adverse effect level of 284, which is in green here, was identified for development toxicity, which is a critical effect in purple, in a subchronic inhalation study on rats, and we got that information from the ACGIH. We applied an uncertainty factor of 10 to account for the limitation and duration, so it was a subchronic, and interspecies variation. A TWA of 20 ppm, even though we were rounding down in the situation, was recommended. And this was considered sufficiently low to protect for the developmental toxicity effect. So let's just have a quick look at the study over here. This is kind of interesting. So rats were exposed at these doses. So a group of rats was exposed at 0. They're your control group at 284 ppm. These are the equivalent milligrams per meter cube, but I'll just talk to ppm. 284, which is your null. A group of rats were exposed at 710, and the last dose group was 1,420 ppm. They were exposed for 6 hours a day for 7 days a week. Because it was a developmental study, the females were exposed in these days of the first 19 days of gestation, and the males for 51 days. Oh, I've just noticed time. I'm getting behind time. We applied the uncertainty factor. We came up with that number. Okay, I'll move through to the stells or peaks. Again, a flow chart. There were some certain factors that we would use to favour a peak over a stell. I won't go into that too long because I really realise we're running out of time fast here. But generally, the peak limitation of stell value will be higher than the TWA. If there were chronic effects, that's the TWA, occurred at concentrations greater than those causing short-term or acute effects, there'd be no need to assign a TWA. But if the concentrations are only marginally different, we would assign the lower of the two values, the chronic and the short-term value, to a short-term or acute stell or peak. So the peak, I will jump back. The peak was favoured if the health effect was severe, if the health effect was immediate, intolerable, or irreversible, or there was a very steep dose response concentration or dose response relationship. And the derivation of the number was very similar to the TWA. So then we had to, we had a chemical where it required a TWA and a stellar and or peak. We had to determine what combinations were appropriate. This is part of the flow chart. Here are the combination of potential parameters. As you can see, TWA, stellar, peak limitations by themselves. TWA endostel or TWA and a peak limitation. They were the 5 combinations. You couldn't have a stel and peak limitation together at the same time. Stage 5 notations. Okay, running short of time here. The first 3, the carcinogenicity notation and the sensitizer notations, were informed via the HCIS database, which was based on globally harmonized systems of classification for labeling of chemicals, GHS. The difference between the GHS carcinogenicity is that the category 1 and 2, according to the GHS, did not specifically differentiate from the genotoxic and non-genotoxic carcinogens. We also had to assign skin notations where possible, and the new immediate dangerous to life or health notation. This is the notation flow chart. I'll jump through that. Skin notations. The wares are generally protective of toxicity by the inhalation route. However, dermal exposure to some airborne chemicals may also contribute to systemic effects. A skin notation is assigned based on evidence of systemic effects that would contribute to the inhalation route effects via the inhalation route by the dermal route. So there had to be dermal uptake and systemic effects. The information from this came from workplace, human data and animal data, also in vitro and in silico data, which were estimations performed via a computer. Here's the criterion. I'm sorry, I'm running out of time. Apologize. Go to the guidance values and you can look at that in more detail. Here is the hierarchy of evidence. Human studies, workplace studies was sufficient in isolation to assign a skin notation. Remember, skin notation is evidence of systemic effects from dermal uptake in contribution to the inhalation. Quick example, here's some evidence in the appendices for acrylamide. And we also received a Excel spreadsheet decision-making model, I guess, to help us with the decision. So in red, there was evidence in human subjects, peripheral neuropathy. So in the spreadsheet, there'd be drop down yes or no. We'd put that in there. It was yes. So therefore, because it was from human data, skin notation was warranted on that. Just say that wasn't there. I'll just give you a demonstration of some more. Here's some in vivo data. Your single exposure study, an LD50, as mentioned before, was 1,148 milligrams per kilograms in rabbits. That we popped that into the spreadsheet. It was less than 1,000, which is the criteria, the cutoff point, which means no. And there's also some dermal absorption rates there, 40 to 30%, which was in rats, and that really dropped in there. But regardless, because of the human evidence, a skin notation was warranted. I was going to talk a little bit about the future, but like 10 seconds. That theme of collective learning and increasing complexity in our world, in our environment. We have machine learning, increased algorithmic sophistication, combined with increased power means a big data, collection of this data. I'm sure you're all quite aware of this. We're going to have smaller sensors. We have phones. We've got citizen science. We're going to have possibly biometrics in the future. It's a more complex society. There's also going to most likely changes in job structures and roles, and this will be important for occupational hygienists. And some jobs will go, machines will take over some of the more hazardous jobs. And there will be new material and use hazards as we see evolving at every point. I want to say that's the end of presentation. Sorry, I had to rush through a bit. There was a lot to cover there, folk. I want to say a big thank you to the AIOH, the WSP team, Nathan Redfern, Kai Byes, Osaf Ahmed, Peter Aspinall, Sam Gid, and also we had some assistance from colleagues over in Canada. A big shout out to Safe Work, particularly Jackie Shepherd and the team. They were great. It was a lot of fun working with them. And I also want to thank everyone who has joined us today. Bo, that's it for me there. What do we got? We got 2 or 1 minute maybe for a question. I'm not sure where we're at.
Sure. We've got a question here from Gavin Wellings.
Yep.
Appreciate this is a daunting project. Can you provide an overview of the size of research team involved in reviewing the 726 chemicals?
There they are there. I'm not one to be, I'm usually pretty modest. I did the lion's share but never would have accomplished this at all without these guys. It was definitely a team, and the assistance from the peer reviewer, not assistance, the informed information received back from there. Any other questions?
Yes, we've got one from Anonymous. Are there any SWA guidelines for indoor air quality in a typical office workplace, specifically for VOC, from carpet and indoor furniture and fit outs and dust/particles? If not, why?
I can't speak to that really. I don't, to be honest, I'm not sure if someone who's knowledgeable about that could pop that answer in the question and answers. I'm not sure why not, and I don't think we would need to look at the exact source. I apologize, I can't. I don't have the knowledge to answer that right now.
One more?
Yeah, sure, go for it. I'll take as many as you want from now on.
Yeah, great. Okay, what approach was used where there was conflicting data in primary and secondary sources, noting original data from the trusted source were not reviewed?
Okay, so great question. I had to cull this out of my presentation. We had a few options. We could amend the WES. We could set an interim. So if there was some uncertainty involved, we would send it into interim WES or TWA, and then recommend either a priority review at the next scheduled review of that particular chemical, or a more in-depth assessment outside of that process. But that would only be recommended if we had some idea that the information was out there in the scientific literature. The other options we had, we had amend, a new one where there wasn't a safe work TWA, interim, as I just mentioned. I can't remember the others off the top of my head right now. I'm sorry. Yeah, so I hope that answers your question.
Next question.
Sure.
How do you use WOE or WO only using primary sources without looking at the quality of the background studies?
The part 1 of the overarching methodology set by Safe Work Australia, we had to rely on the fact that their criteria for picking the primary sources that they sourced, and the criteria was robust enough that the primary sources information was usable and was robust, and we were I wouldn't say confined, but we were bound by those rules, I guess, and that was the logic behind it. So the criteria and identification of the primary sources established that information was usable.
Next one. This one was actually asked back at 12:31, so I'm sorry, Halil, if this is not relevant later down the track, but it was, the question here is, has the ability to analyse to the recommended levels been taken into consideration in establishing the proposed standard?
In short, no. We derived the numbers based on the science, based on those methods. We either the risk base using the 1 in 100 acceptable risk level, derived it from that, or the threshold value as explained. So we derived the numbers, and then once those derived, there was consideration of the measurement. I'll just try to find, oh, here we go. And if you look here where it says sampling and analysis, we would derive the value, and then we'd make a broad review that if it was quantifiable or not. So this one, the value was quantifiable. If we look at where's vinyl chloride, that's somewhere up here, wasn't it? There we go. 7 parts per billion. If you look here, sampling analysis, there is uncertainty regarding the quantification. So that's the only, when it comes to measurement of the airborne chemical hazard, that's as far as we went, not in the derivation of the number.
Okay, another one from Deborah Glass. TWA usually come down when they change because there is new data. Shouldn't the most recently updated value be used?
We used the most updated value in the sources that we used in the primary sources and the data and the evidence within those primary sources. So the ACGIH was the 2018 released set of ACGIH papers. Yes, I think some of them even went up based on the evidence, as whatever the evidence at hand within those primary sources that was available, provided, whatever evidence provided, we adjusted according to that. So I think there was some that went up, to be honest, if I recall. It's been a while now. So yes, we tried to use the most recent data.
One more, and this will be the last one.
Sure.
Do the limits of detection for lab analysis play much as a part in the reviews, especially large reductions like ISO? I knew
that's okay. Yeah, that's okay.
Isocyanates and hexavalents.
Hexavalent chromosome. Yeah, I stumble over. I'm amazed I didn't stumble over some of these words in this discussion. I think I answered that's been answered before. Here with the sampling and analysis, no. To straight up, no, that was not considered. In the derivation of these values. Now, it was considered after the values have been derived. So we had a very scientifically robust method to derive these values. Now, as mentioned before, the sampling analysis was of that derived value was looked at after the fact, and it did not influence the number that we recommended. Now, they're recommended, so remember these are up for public comment to discuss primarily the scientific aspects of that. So if you want to have your say and be part of this, get in there and respond to those evaluations. So in short, sampling analysis, no, it didn't affect our numbers.
Okay, that concludes the end of the webinar. Thank you so much, Nathan.
Thanks, everyone.
Thank you, everyone. We hope you enjoyed the webinar, and we'll see you at the next one.
See you guys.
See ya.